Hello and welcome back. In our previous videos, we've looked at simple linear regression where we had one regressor variable and one response variable. But what happens if we have multiple response variables? For instance, I'm going to read in the Bayes data set. There are actually multiple regressor variables here. We have sex, we have head length, we have head width, we have neck size, we have body length, we have chest width, and we have weight. And what we would like to do is see if we can predict weight based on these other regressor variables. So here weight is our response variable, and the rest of these are regressor variables. This data is a simulated data set from Triola. This is on the repository that you will find a link to in the video. Now what we've done, I've called this YLM. And remember, this LM says it's a linear model, and I'm going to model Y against X. But notice Y here is weight. And then my X variables are all included here except for sex. And so I want to see if I can model weight using head length, head width, neck size, body length, chest width. And here I'm calling the data set Bayes. And so what do we get? Well, if I run this model, then I highlight YLM. What I get are my coefficients for my estimated parameters. Now, in a multiple linear regression model, what we get is y hat is beta hat 0 plus beta hat 1 x1 plus beta hat 2 x2 plus ... plus beta hat k xk plus epsilon ij. And here, what we're saying is our expected value of y, which is y hat, that's equal to beta hat 0 plus beta hat 1 x1 plus beta hat 2 x2 plus ... beta hat k xk plus epsilon ij. Keeping in mind, epsilons are still normally distributed, independently and identically distributed. And so epsilon I does not equal epsilon j. It's independent. How do we go about analyzing this? Well, the first thing we need to do is conduct a global F-test. So we need sum of squares regression and sum of squares residual. And so our global F-test is going to equal the sum of squares regression over k, the number of parameters in the model, divided by the sum of squares residuals over n minus k plus 1, where n minus k plus 1 is the residual degrees of freedom. So in order to find these sum of squares regressions and sum of squares residuals, we're going to do an AOV function of YLM. And what this is going to give us is the sum of squares for each of our regressor variables and the sum of squares of our residuals, along with the residual degrees of freedom. Now, sum of squares regression is simply the sum of all these regressor sums of squares. Now, sum of squares regression is 684,997. Now, my sum of squares residuals we already see here, 95,797. K here, the number of parameters in the model, is going to be 5 because we've got head length, head width, neck size, body length, and chest width. And so K is going to be 5. Likewise, our residual degrees of freedom is 132. That is 138 minus 5 plus 1. And so if I decide that I want to do a global F-test using what I'll call the long method, I have my sum of squares regression divided by my K parameters, divided by my sum of squares residual over the residual degrees of freedom. And what I get is 188.7678. Now, if I want to do a global F-test here, notice I've got my F value, I've got my regression degrees of freedom, my error degrees of freedom, lower tail is false, and what we get here is 2.491945 e to the negative 58. That's a really small p-value. But I can also do this using the summary of my linear model. And notice, right here, my F statistic, 188.8 with 5 and 132 degrees of freedom and a p-value of 2.2 e to the negative 16. This is as small as it's going to get it. Now that we've checked our F statistic and its p-value, and we see that p is less than alpha, we know that our global F-test says that we have a usable model. What about testing our individual variables? Suppose we simply look at head length. Our estimate is negative 6.751. Our standard error, 3.462. And if you recall from previous videos, our t is simply our estimate over our standard error. And so what we get here is that t is negative 1.950029. And so if I were to look, I get 0.02664787. If we go up to our actual summary, we can see that the summary gives us a p-value of 0.0533. Well, why is that? We came up with something completely different. We came up with 0.02664787. And this is because our summary statement has given us the probability that we're greater than the absolute value of t. That means it's giving us a two-tailed probability. Well, here we've looked at the probability we're in the lower tail. So the probability we are less than negative 1.950. And so this is going to be half of the p-value that we observed in our summary statement. Therefore, R has given us the absolute value of t. It gives us the probability of a two-tailed test. To do a one-tailed test, take the absolute value, divide by 2. What about confidence intervals? We very well may want confidence intervals on our estimates. And so the first thing we want to do, again, we're going to look at our point estimate plus or minus our margin of error. Well, our point estimate is going to be beta I. Our margin of error is t star times the standard error of beta I. So suppose we wanted a 99% confidence interval for next size. Well, notice I want 99%. So my t star here is 0.995. Why 0.995? Because I'm looking at what's below. So 99% means that there's 1% left over. That's a 0.5% in each tail. So if I run this, I see that my t star value is 2.613588. Now notice here that I'm doing next size, so 7.726 is my value for beta I. My standard error for beta I, 1.258. And so if I look at my lower interval value, beta I minus my standard error, 4.438106. And then if I look at my upper interval value, 11.01389. Now, there's an easier way to do this. If I use the function conf int, and I do this on my YLM, and I put my level in of 0.99, remember, we were looking at next size. And so let's take a look at what next size gives us. 4.439063, 11.013216. So we're off at the 4th decimal place. And this is just rounding. Okay, that's it for this video. In the next video, we'll look at subsetting the model because, as you can see, when we run our summary, several of these, depending on the alpha we use, but in particular, body length and head width, look as though they may not be necessary for the model. So can we subset the model and determine if these variables give us any useful information?